Hello, welcome back to Chapter 2 in Materials Kinetics. Today, the topic of the lecture is Irreversible Thermodynamics, which is the subfield of thermodynamics that is used to describe non-equilibrium systems. It is also what gives us the thermodynamic driving force for kinetic processes. So today, we are going to cover what are reversible and irreversible processes, affinities, fluxes, entropy production. This forms the basis for irreversible thermodynamics. Then we are going to make three simplifying assumptions, which are a purely resistive system, a linear system, and what's called Onsager reciprocity. And then we'll quickly go through some specific examples of applications of irreversible thermodynamics. So recall last time in Chapter 1, we classified processes as being spontaneous or non-spontaneous. A spontaneous process was one that went from a higher Gibbs free energy to a lower Gibbs free energy, or in other words, from a less thermodynamically stable state to a more thermodynamically stable state. So spontaneous processes having a negative delta G, a negative free energy of the reaction. On the other hand, a non-spontaneous process is the opposite. A non-spontaneous process goes from a more thermodynamically stable state to a less thermodynamically stable state. So the delta G increases, and these do not happen on their own. They would only happen if you perform work on the system. Now, remember also that whether a process is spontaneous or non-spontaneous only tells you about the difference of the Gibbs free energy between the initial and final states. It doesn't tell you anything about the height of this barrier. So it doesn't tell you anything about the kinetics of the process and whether you would actually see this process occur on the time scale of your experiment. An example of a spontaneous process that we do not see routinely is the spontaneous conversion from diamond to graphite. So that involves a lowering of the Gibbs free energy of the system under ambient pressure and room temperature. However, the barrier for that to occur is so large that we do not observe it in practice. Now, another way that we can classify thermodynamic processes is whether they are reversible or non-reversible or irreversible. So reversible processes are the ones that are most often studied in thermodynamics. For a reversible process, the system can be restored to its initial state from the final state without producing any changes in the thermodynamic properties of the universe. In other words, a reversible process is one that kind of has an undo button, that if you hit it, you could just sort of go back to where you started, and it's as if nothing ever happened. For a system to undergo a reversible change, the process should occur infinitely slowly and due to an infinitesimal gradient. In other words, it has to be the smallest perturbation possible, and it has to be done over an extremely long timescale. During a reversible process, all of the changes in state that occur in the system are in thermodynamic equilibrium with each other. So during this reversible process, the system never leaves equilibrium. And if the heat content of the system remains constant during a reversible process, which means that the process is also adiabatic, then the reversible process is also an isentropic process. In other words, the entropy of that system would also remain constant. And the phenomenon of undergoing a reversible process is called reversibility. What would be an example of a reversible process? Let's suppose that we have a gas here with this lid on it that can go up and down in response to pressure, and that we drop one infinitesimally small grain of sand at a time onto this to compress the gas, giving the system plenty of time to respond to that infinitesimal perturbation of the single grain of sand being put on top of it. So if we drop one grain of sand at a time, we can go from this initial uncompressed state A to the final compressed state B. And then if we remove one grain of sand at a time, if we take our little tiny tweezers and remove one infinitesimally sized grain of sand at a time, allowing the system to respond over an infinite amount of time, then we can restore the original state of the system A without leading to any changes in the state of the universe. This is a reversible process because each perturbation, each grain of sand, is so tiny, and because we took an infinite amount of time to do that. An irreversible process, on the other hand, is where the initial state of the universe cannot be restored from the final state. So there's no undo button with an irreversible process. During an irreversible process, the various intermediate states of the system are not in equilibrium with each other. The entropy of the universe increases during an irreversible process and cannot be reduced back to its initial value. And one of the key themes of irreversible processes is that an irreversible process is an agent of the second law. An irreversible process leads to an increase in the entropy of the universe, and there's no going back. Also, the phenomenon of a system undergoing an irreversible process is called irreversibility. What would be an example of that? If we take our identical initial state here, A, of this uncompressed gas, and rather than carefully dropping a single grain of sand at a time, we just drop an anvil onto the compressed gas. There's a very drastic departure from equilibrium as the system responds to this. And so this would be a dramatic example of irreversibility compared to the very gentle reversible process. So if we consider, say, our uncompressed state here at higher volume, lower pressure, versus the compressed lower volume, higher pressure state here, we can get to this by any number of irreversible paths. So with dropping an anvil, this increases the pressure right away, and then the volume responds after that. And there's any number of irreversible paths to connect these two, but only one reversible path. That would be this, where the system is in equilibrium along all of these intermediate states in between the initial and the final state. So one reversible path and any number of irreversible paths. Now, in comparing reversible and irreversible processes, for a reversible process, it is carried out infinitely slowly. On the other hand, for an irreversible process, it is carried out rapidly, by which I mean finite time. So a reversible process takes infinite time for completion, whereas an irreversible process takes finite time for completion. With a reversible process, the system is always in equilibrium at all stages of the process. And for an irreversible process, the system departs from equilibrium at some point during that process. For reversible processes, the system can return to its initial state without changing the thermodynamic state of the universe. For an irreversible process, that cannot happen. You cannot go back to the initial state without changing the thermodynamic state of the universe. For a reversible process, the entropy of the universe remains constant. For an irreversible process, an increase of entropy is required. So if we consider the statement of the second law, that the delta S is greater than or equal to zero, the equal to zero part refers to reversible processes. The greater than zero part refers to irreversible processes. For a reversible process, maximum work can be obtained because the delta S is equal to zero. And for an irreversible process, the work that is obtained is never a maximum because of the production of entropy. Which one of these is realistic? Reversible processes are great for considering ideal situations, like in thermodynamics textbooks, but almost all real processes that we observe are irreversible processes because they do involve going out of equilibrium, sometimes by a lot, sometimes by a little, and because they occur over finite time scale. So irreversible thermodynamics then is critically important for us to understand real processes that occur. Now, the person who invented this field of irreversible thermodynamics is Lars Onsager. He lived from 1903 to 1976. He was a Norwegian-American chemist and physicist. When he first came to the United States, he became a faculty member at Johns Hopkins University in 1928. Unfortunately, it was reported that he had a difficult time, quote, connecting to lesser intellects or communicating with lesser intellects, and he was let go after a single semester. He moved to Brown University in Rhode Island, where he then published his groundbreaking work on irreversible thermodynamics from 1929 to 1931, which is what we're talking about today in this lecture. Unfortunately, just like Boltzmann's pioneering work in statistical mechanics before him, Onsager's work also went unnoticed for about 20 years, probably because it was such a novel concept, but his papers were also rather impenetrable from an understanding point of view. So it was very difficult for other people to understand what he had done. Fortunately, his story ends a lot better compared to Boltzmann's, and that his work was noticed. And later on, he actually earned the Nobel Prize in Chemistry for this work that we are discussing today. He won that in 1968. But from Brown, he moved on to a postdoc position at Yale. When he showed up at Yale, it was discovered that he didn't actually have a PhD yet. And of course, you can't be a postdoc without having the doc part. But fortunately, at Yale, they let him stay. He earned his PhD at Yale and then spent the remainder of his career there and did all kinds of outstanding research. And as I mentioned, also got the Nobel Prize in Chemistry for this work in irreversible thermodynamics. So what I'm going to try to do with this lecture is to make this topic of irreversible thermodynamics as accessible as possible for all of you. This is the lecture that definitely took me the most time to put together because a lot of the material that is published is difficult to understand, and some of it is just outright incorrect in the literature as well. Chapter 2 in the book, which covers this, also took me more time than any other chapter in the book because I wanted to make it accessible and correct at the same time. So I'm hoping that I've been able to achieve that. Now, the first key quantity in irreversible thermodynamics is called the affinity. The affinity is the thermodynamic driving force for an irreversible process to occur. And affinity is denoted with the capital F, F indicating that it is a thermodynamic driving force. And affinity is defined as the change of the entropy of the universe as a result of changing some thermodynamic coordinate x of the system. So in other words, if there is an opportunity to adjust the thermodynamic state of the system somehow by adjusting some thermodynamic coordinate x, whether it's volume, internal energy, any parameter whatsoever, if the entropy of the universe can be increased as a result of that, that means that this affinity has a non-zero value, which means that there is an opportunity for the system to undergo an irreversible process to increase entropy of the universe and therefore act as an agent of the second law of thermodynamics. On the other hand, if the affinity is zero, that means that we already have an equilibrium system and that there's no way to change its thermodynamic coordinates to increase entropy. So if the affinity is zero, then we do not have an irreversible process. If the affinity is non-zero, then there is an opportunity for an irreversible process to occur to move the universe a little bit closer to equilibrium. Now, let's consider the affinity of a simple composite system here that is composed of two subsystems. So if we've got a left subsystem here that has some extensive thermodynamic parameter x1, and then on the right-hand side for the second subsystem, it has a thermodynamic parameter x2. And because they're extensive, the x1 plus the x2 gives you the total x of the subsystem. And if this quantity is basically conserved across across the total system, then this x1 plus x2 is equal to a constant, which means that if x1 increases, then x2 decreases by the same amount, or vice versa. Now, the equilibrium values of x1 and x2 are determined by a vanishing of the affinity. So using our definition of affinity, the affinity here, F, is defined as the change of the entropy with respect to changing some thermodynamic coordinate of the system. So let's arbitrarily pick that to be x1, and this is done under a constant x naught, so constant total x for the entire system. The entropy here can be expressed as the entropy, the summation of the entropies of the subsystem. So S equals S1 plus S2. And then since the change of the x1 is equal to minus the change of the x2, given that the total x here is a constant, that means that this can be written as the partial of S1 with respect to x1 minus the partial of S2 with respect to x2, because any increase of x1 leads to a decrease of x2. So that's how we pick up the minus sign here. So what does this mean? If this is our affinity, the affinity is equal to this partial of S1 with respect to x1 minus the partial of S2 with respect to x2. If this affinity is equal to 0, then the system is in equilibrium because there's no opportunity to drive the system towards a more thermodynamically favored state. On the other hand, if the affinity is non-zero, then an irreversible process occurs, which can take the system towards the equilibrium state. So it all has to do with whether this first term is equal to this second term or not. If they're equal to each other, then the affinity is 0, and there's no irreversible process. If they are different from each other, if these two subsystems are different, then an irreversible process will occur until these two terms end up being the same, at which point the irreversible process has completed and equilibrium has been obtained. Let's consider an example of this. So if we consider two subsystems here that are separated by a diathermal wall, diathermal means that it allows the transfer of heat, but not the transfer of matter. And let's consider that our thermodynamic parameter of interest is the internal energy, U. In that case, the X here becomes a U, so the affinity is the partial of S1 with respect to U1, so the partial of the entropy of subsystem 1 with respect to the internal energy of subsystem 1, minus the same thing for subsystem 2. This, using our handy-dandy thermodynamics textbook, we know that the partial of the entropy with respect to the internal energy is the reciprocal temperature. The entropy here has units of joules per Kelvin. The internal energy has units of joules, so the joules cancel, and what you're left with is 1 over Kelvin, which means 1 over temperature here. So 1 over T1, this is the reciprocal temperature of the first subsystem, minus the reciprocal temperature of the second subsystem. So 1 over T1 minus 1 over T2. How do we know if the system is in thermal equilibrium? We know that the system is in thermal equilibrium if the affinity is 0, meaning T1 equals T2. If the temperatures are the same, then we've achieved thermal equilibrium and there won't be an irreversible process. On the other hand, if the temperatures are different, that means the affinity is non-zero, and the affinity then acts as a thermodynamic driving force for, in this case, heat flow between the two systems, which will drive it towards an equilibrium. So if the affinity is the driving force, the affinity is like the cause for an irreversible process, the effect from that cause is the flux. So the flux is the response to an applied force characterized by the rate change of the thermodynamic parameter x. In other words, the flux here, which is usually denoted with a capital J, the flux is defined as being the change of any thermodynamic parameter x with respect to time. Now, many of you have probably used flux being like the change of something per unit area per unit time. That is a specific example of a flux. The most general definition of a flux is simply the time rate of change of any arbitrary thermodynamic parameter x. So J here is defined as the change of x with respect to time. And using this analogy of the affinity being the cause, the flux being the effect, the flux vanishes as the affinity vanishes. So if we lose our thermodynamic driving force for the irreversible process, then we also lose the flux that would be associated with that. And likewise, a non-zero affinity then leads to a non-zero flux. So we already know some of these from our basic physics class. So some common fluxes describing the flow of matter. This would be the flux of matter, which is governed by Fick's first law. Fick's first law was proposed in the 19th century, many decades before Onsager did his work in irreversible thermodynamics. But the basic formulation is still there. You see, we've got some flux of matter. And what is governing this flux of matter? Two things. One is the thermodynamic driving force, which in Fick's first law is a concentration profile of the material. So if this concentration profile goes to zero, then there is no driving force for diffusion of matter to occur, according to this law. If there is a non-zero concentration profile, then there will be a flux of matter that acts to eliminate that concentration profile. And the minus sign here is because the flux acts to eliminate the concentration profile rather than making it get large. And then the rate that this process occurs is governed by this prefactor here, this kinetic rate parameter, which in Fick's first law is the diffusion coefficient d. So dc dx is the thermodynamic driving force here, the concentration profile. Any inhomogeneities in concentration would act as a thermodynamic driving force for the diffusion of matter. The rate at which that occurs is given by the diffusion coefficient d. The minus sign is because the flux acts to reduce and eventually eliminate the concentration profile. And putting that all together gives us the flux of matter. Another common flux equation is Fourier's law. In this case, this is the flux of heat. The thermodynamic driving force is a temperature profile. The kinetic parameter is the thermal conductivity. So the higher the thermal conductivity of the material, the faster the heat will be transferred. And again, there's a minus sign because the flux of heat acts to eliminate the temperature gradient rather than increasing the temperature gradient. This is Fourier's law. You notice the form of the equation is mathematically identical to Fick's first law. It's just Fick's first law deals with the flow of matter. Fourier's law deals with the flow of heat. Otherwise, these equations are mathematically identical and they're solved using exactly the same approaches. Another example is Ohm's law. Ohm's law governs the flow of electrical charge, where here we've got the electrical potential gradient, which is our thermodynamic driving force. Our kinetic factor is the electrical conductivity, or in other words, 1 over the electrical resistivity. Again, the minus sign here means that the flow of electrical charge here acts to eliminate the electrical potential gradient. Again, this is mathematically identical to Fick's first law and Fourier's law. So what do these equations all have in common? They all have a thermodynamic driving force. They all have a kinetic rate parameter. They all have a minus sign, meaning that the flux acts to eliminate the thermodynamic driving force. And they were all proposed in the 19th century, decades before Onsager did his pioneering work in irreversible thermodynamics. So at the start of the next lecture, I'm going to show you how we actually get from Onsager's formulation of irreversible thermodynamics to Fick's first law, several decades after the fact. But the point is that we're all familiar with some of these flux equations already, and we can already see that they all have thermodynamic driving forces and they all have kinetic rate parameters. Now, the affinities that correspond to these three cases, so governing the flow of heat, the flow of matter, and the flow of electrical charge, we need to go back to one of our fundamental equations from thermodynamics expressed in differential form. Specifically, how is the local entropy density changing? And including the appropriate terms here, we've got how the local entropy density is changing with respect to the local internal energy. The prefactor there is 1 over the temperature. So how much does the entropy increase due to changes in the internal energy? The prefactor there is 1 over the temperature. So the affinity then that governs this, the affinity that governs the flow of heat, is going to be whatever gradient that we have in the reciprocal temperature. So the gradient in 1 over the temperature gives us the affinity. And that is what is shown here. Likewise, moving on to the flow of matter, this is what is eventually going to give us Fick's first law. Here, this is how much does the entropy change with respect to a mole fraction of each of our chemical constituents. And the prefactor there is minus the chemical potential over the temperature. And so the gradient here, the gradient of this quantity, is the gradient of minus the chemical potential over the temperature. That is the affinity that governs the flow of matter. That is our thermodynamic driving force that governs the flow of matter. And for the electrical charge, likewise, we use the prefactor here, which is simply minus the chemical potential of the electrons divided by temperatures. So any inhomogeneity there, in other words, any gradient there, gives us a non-zero affinity for the flow of electrical charge. What I'm showing here is in one continuous dimension x, this x derivative here. You can write any of these in terms of the gradient operator as well, which is especially helpful if you're dealing with more than one dimension. And as I mentioned, all of those flux equations were proposed phenomenologically based on experimental data in the 19th century, well before Onsager's development of irreversible thermodynamics. So this common form of Fourier's law here can actually be expressed in equivalent format directly from Onsager's relation using a gradient in the reciprocal temperature compared to the temperature itself, and it all works out fine. In getting Fick's first law, we do have to make a couple of assumptions, and we will do that at the beginning of the next lecture in chapter 3, which focuses entirely on Fick's laws of diffusion. Now, as I mentioned, irreversible processes are agents of the second law. They happen because there is an opportunity to increase the entropy of the universe as a result of undergoing those irreversible processes. And we can see that if we take the time derivative of entropy, so how much is the entropy changing with time, we can expand out this derivative here, this ds dt, in terms of a partial of s with respect to a given thermodynamic parameter, x sub k, times the change of that thermodynamic parameter, x sub k, with respect to time. And then if we sum up over all of the relevant thermodynamic parameters here, that would give us the total rate of entropy production. So how fast the entropy of the universe is increasing with time. Now, these should look familiar by now. This first term here is how is the partial of entropy with respect to a thermodynamic coordinate. That, by definition, is the affinity with respect to that thermodynamic coordinate here, F. And then this latter quantity, the time rate of change of the thermodynamic parameter, by definition, is the flux. And so what we have here is that the entropy production, the rate of increase of entropy with time, is simply the product of the affinity, F, and the flux, J, and then summing up over all the contributions from all the various thermodynamic coordinates that can change. Thus, the rate of entropy production is the sum of the products of each flux with each of its associated affinities. So, now that we've set up some of the basics here, we need to make some assumptions to make the formulation of irreversible thermodynamics a bit more tractable. The first of these assumptions is that we are dealing with a purely resistive system. A purely resistive system is one in which the fluxes at a given instant in time depend only on the values of the affinities at that same instant in time. In other words, you don't have to go back to some previous time and take the affinities from some previous time to determine the fluxes right now. This term, purely resistive, actually comes from electrical engineering, because an example of a purely resistive system would be an electrical circuit that has only resistors and no inductors or no capacitors, because inductors or capacitors give the circuit memory. And if the system only has resistors, no inductors, no capacitors, then it doesn't have a memory. So purely resistive then means that the fluxes at this given instant in time only depend on the affinities at the same point in time. Now, with that assumption, what we can do is expand the flux of a given thermodynamic parameter I. We can expand this flux J sub I in terms of the affinities of all the different thermodynamic parameters in the system. And those affinities only depend on the same instant in time. We don't have to go backwards in time. So we can expand the flux in terms of these affinities using a Taylor series expansion, and remembering then that the flux is zero if the affinity is zero. The first term of the Taylor series is zero, which means that the Taylor series is actually a Maclaurin series. So Maclaurin series is a Taylor series where the first term is zero. And so what we're left with here, the first non-zero term, is the linear term, where we have a summation here over all the thermodynamic properties of the system, all the thermodynamic coordinates, the affinities of each of those thermodynamic coordinates, F sub j, and then the prefactors out in front, L sub ij. So we've got a ji, this is the flux of thermodynamic parameter I, and it could depend on either its own affinity I, as well as depend on the other affinities that are also acting in the system. So we sum up over all of those affinities, summing up over J, and the prefactors are reflect both of those indices here. So it's Lij. These Lij's, you can see by definition, it's the change of the flux of I with respect to changing the affinity of J, where we know that if the affinity is zero, that the flux would also be zero. So this partial derivative of the flux of I with respect to the affinity of J is Lij, and this is what's called a kinetic coefficient. It's telling you how big of an effect that the affinity of J has on the flux of I. If there's no effect, then the kinetic coefficient would be zero. The larger the kinetic coefficient, the greater the effect that we have there. Now, that's the first term of the Maclaurin series, the linear term. If we continue, we can get the quadratic term. The quadratic term involves 1 over 2 factorial times now a double summation over pairwise combinations of our thermodynamic coordinates. So this would be a product of the affinity of J times the affinity of K, and then the coefficient would have 3 indices now, Lij, K. And this, as you can see, it would be a second derivative. So the second derivative of flux of I with respect to changes in both Fj and Fk. So what is the second derivative here of the flux of I with respect to changes in the affinity of J and the affinity of K? This is what's called a second order kinetic coefficient. In principle, we could continue this on. There could be a cubic term with a 1 over 3 factorial times a triple summation and third order kinetic coefficients, a quartic term with 4-body interactions, and so on. However, the reason that we do Taylor series or Maclaurin series is that the importance of each term becomes less and less. So the dominant term is the linear term. The quadratic mixing term here is less important. The cubic term is even less important than that. And what this means is that we can truncate the Maclaurin series after a certain term. And what we're going to do with our second assumption, after this purely resistive assumption, the second assumption is the assumption of linearity. We're going to truncate this Maclaurin series after this linear term and assume that everything here is captured in the linear term. And that is typically a good assumption if we're not too far outside of equilibrium. If we have undergone a really large departure from equilibrium, then that may not be true. We may need to include additional terms. But for the sake of simplicity, we're going to assume linearity, and we're going to keep this first term and then truncate the remaining terms. So what we have then is a linear, purely resistive system. When the affinities are small, quadratic and higher order terms of the Maclaurin series can be neglected, and this gives us now this linear relationship for a linear, purely resistive process, where J sub I, the flux in I, is now just summing up over all of these linear terms of each of the affinities F sub J and the corresponding kinetic coefficients L, I, J. This approximation is suitable for systems that deviate only slightly from equilibrium. Now, if we write this out for all of our different types of fluxes, let's suppose that we've got omega number of thermodynamic coordinates. We would have an equation for the flux of the first thermodynamic parameter, J sub 1, an equation for the flux of the second one, J sub 2, J sub 3, and so on all the way to J sub omega. And for each one of these fluxes, we would have the contributions from each one of the affinities of the system. So this would be J1, the impact of its own affinity here, F1, with its kinetic parameter L11, the impact of the affinity of the second thermodynamic parameter, F2, with the coefficient L12, the third parameter, and so on through the omega parameter. And so we set up then this system of linear equations that can describe all the fluxes for all the thermodynamic parameters in terms of all combinations of affinities. And this naturally leads then to the formation of this kinetic coefficient matrix, this L matrix, which would have all of our kinetic coefficients that describe all of these coefficients here in this set of equations. And you'll note that along the diagonal here, we've got all of the terms that have the same indices, L11, L22, L33, and so on. These are the kinetic coefficients that give you the flux from the affinity of its own value. This is what's called the direct coefficients. This is the affinity leading to a flux in the same thermodynamic coordinate. And then all of these off-diagonal terms are what's called coupling coefficients. This is what leads to an affinity and one thermodynamic coordinate giving a flux in a different coordinate. So for example, we're going to cover some examples later in the lecture, but an example would be maybe creating an electrical current if you impose a thermal gradient on the system. This is called the Seebeck effect. Or piezoelectricity. If you perform mechanical work on the system, that you can generate electricity. It's conversion between different types of energies or transfer of momentum between different types of particles that leads to these coupling effects where an affinity in one type of thermodynamic quantity can lead to a flux in another type of quantity. So these direct coefficients here along the diagonal, these direct coefficients link each flux to its own affinity. In other words, its conjugate driving force. Conjugate meaning it's the same thermodynamic parameter in both the affinity and the flux. All of the off-diagonal terms, these coupling coefficients, these are responsible for coupling effects, also known as cross effects, and this results from the momentum transfer between different types of species, so maybe different types of atoms, or transferring momentum to electrons, photons, whatever. And these cross effects then give these processes that really can only be captured via irreversible thermodynamics. Now, our first two assumptions were purely resistive system and linearity. The third and final assumption that we are going to make is the Onsager reciprocity theorem. The Onsager reciprocity theorem states that for the kinetic coefficient Ljk, this is equal to the same kinetic coefficient, but then switching the indices, Lkj. Or in other words, writing out these kinetic coefficients in terms of the partial derivatives, the partial of the flux of K with respect to the affinity of J would be equal to the same thing where you've just switched the J and K coordinates. And this theorem defines the fundamental symmetry of irreversible processes. An example of this would be in the context of thermoelectric materials, there's the Seebeck effect, where if you're imposing a thermal gradient on the system, it can produce electricity. The opposite of that is the Peltier effect, where if you impose an electrical potential gradient, you can generate a thermal gradient. So in one case, you're moving from a thermal gradient to an electrical current. In another case, you're moving from an electrical potential gradient to the flow of heat. The fundamental symmetry here is that the magnitude of that coupling effect would be the same, assuming that Onsager reciprocity theorem is valid. So what are the implications of the Onsager reciprocity theorem? If we take this equation here and just say it verbally, what this is saying is that the change in flux of some quantity caused by changing the direct driving force for another is equal to the change in flux of the second quantity caused by changing the driving force for the first. Some people may be easier to understand in words, other people may be easier to understand in mathematical terms. But in either case, the theorem is based on an assumption of microscopic reversibility for systems near equilibrium. In other words, the time average between a driving force of type J and the fluctuations of quantity K is identical to switching J and K. What does this mean for us in terms of our kinetic coefficient matrix? Is that originally we started here with L11, L12, L13, and then moving down, we'd have L11, L21, L31. What this means is that this kinetic coefficient matrix is symmetric, where the L21 is equal to L12, the L31 is equal to L13, and so on. And so this assumption of Onsager reciprocity makes our kinetic coefficient matrix symmetric. It also dramatically reduces the number of free parameters that we have and simplifies the description of coupling effects for irreversible processes. So to summarize these three simplifying assumptions, the first was a purely resistive system, that the fluxes at a given instant in time depend only on the value of the affinities at that instant in time. The second assumption is linearity. When the affinities are small, quadratic and higher order terms from the Maclaurin series can be neglected, keeping only the linear terms. And then the third assumption is Onsager reciprocity, which is the fundamental symmetry of these kinetic coefficients. So Ljk equals Lkj. So let us finish up this lecture with a few examples of why irreversible thermodynamics is so important, considering these coupling effects. In the next lecture, we go back to Fick's first law, and we'll derive that. At the end of this lecture, I want to focus on examples of coupling effects in some real material systems. The first one I want to deal with is thermophoresis, also known as the Soret effect. This is where a thermal gradient produces a concentration gradient. Next is thermoelectric materials, starting with the Seebeck effect, where a thermal gradient produces an electrical current, and a Peltier effect, where an electrical potential gradient produces the flow of heat. The Thomson effect, where there's a temperature-dependent Seebeck coefficient, also electromigration, where an electrical current produces a concentration gradient. There's also piezoelectricity, where mechanical work produces an electrical current. So there's all kinds of examples of these processes that can occur. Starting with the Soret effect, or thermophoresis, the presence of a thermal gradient in a system can cause the flow of matter. In an initially homogeneous multi-component solution, the presence of a temperature gradient can cause relative movements of the components. In other words, the imposition of a temperature gradient can cause unmixing of these components. So if we have a system here that has two different types of particles in it, the smaller purple particles, the larger blue particles, and if they are initially homogeneous, but then we apply a temperature gradient to it, where there is now a hot end of the system and a cold end of the system, the imposition of that temperature gradient can cause an unmixing of the system. So it can cause the initially chemically homogeneous system to become unmixed, where the larger particles tend to congregate towards the colder end, and the smaller particles tend to migrate towards the hotter end of the system. The reason that this occurs is, of course, at the higher temperature side. The higher temperature means that the particles are moving with a higher velocity. That means that they're hitting each other with greater momentum. And which particles are more likely to get hit? The larger particles are a bigger target, so the larger particles are more likely to get hit compared to the smaller particles. And so they're more likely to get here with greater force at the hot side, where there is more thermal energy, and that causes the larger particles to get pushed towards the colder end more than the smaller particles. And therefore, we get the segregation that appears with these smaller particles aggregating more towards the hotter end and the colder particles migrating towards the colder end of the system. So this, the only reason that this demixing occurs is because of the imposition of this thermal gradient. According to Fick's first law, this would not occur because if we're starting with no concentration gradient, there wouldn't be any flux of matter. But accounting for this coupling effect, this Soret effect, we can get the flow of matter as a result of a thermodynamic affinity in a different quantity. So in this case, the affinity is coming from the temperature gradient, and the effect is on the flow of matter. So if we use what we've just learned to construct the flux equations here for the Soret effect, we have two relevant equations. The first equation is the heat flux equation, this J sub Q. This is the flux of heat. And the second relevant equation governs the flux of mass, the J sub M. And we've got two terms here for the two different types of affinities. We've got our thermal affinity here, which is our gradient of the reciprocal temperature. This is our thermal affinity here, the F sub Q. The affinity from a heat perspective is the gradient of the reciprocal temperature coming from our, how much the local entropy is changing, with result in locally changing the internal energy, as we saw before. The constant of proportionality between those two quantities is 1 over temperature, and therefore that is the affinity here, any inhomogeneity in the reciprocal temperature. That is our thermal affinity. And we've got the prefactors for that, the LQQ. This is the thermal affinity acting on the thermal flux, so that's the LQQ. The thermal affinity acting on the flux of matter is LMQ. Then the other affinity that is relevant here is the mass affinity, and this is governed by minus the chemical potential over the temperature. So any inhomogeneities in the negative chemical potential over the temperature, that gradient is what gives us the mass affinity. And then we've got the kinetic coefficients out in front. So the LQM would be how the mass affinity here affects the heat flux, and the LMM is how the mass affinity affects the mass flux. So we've got our two direct terms here across the diagonal, and then the coupling effects in the off diagonal shown here. This is the basic setup. Now, what you do with this depends on what it is that you want to solve for. If I just give you an example, coupling effects there. If I just give you an example of what if we consider the steady state condition where the flux of the mass goes to 0, what would be the heat flow in that case? And you can do the opposite as well. But just showing you an example here, the steady state condition for where there's no flux of matter would be taking this flux equation for the flow of mass, setting it equal to 0. If you set it equal to 0, you can bring one term over to the other side, where those two terms would then be equal to each other. And therefore you can solve for example, the chemical potential gradient here in terms of the gradient of the reciprocal temperature, getting this ratio of the kinetic coefficients out in front. If you take this relationship, you can plug it back into the flux equation for heat, the JQ equation, and then you can simplify that equation a bit, because now you've got both terms described in terms of the gradient of the reciprocal temperature. The two prefactors here can be combined So you've got LQQ minus LMQ times LQM over LMM, and then just this gradient here in the reciprocal temperature. If we apply Onsager reciprocity, that means the LMQ is equal to the LQM. So you can take either one of them and square it, and then you've got one less parameter that you have to deal with. And so this tells you what the flux of heat would be, assuming that you've achieved steady state with respect to the mass flux. This is just an example of things that can be done using these equations. Another common example of coupling effects in irreversible thermodynamics is the Seebeck effect. The Seebeck effect is a thermoelectric effect where the flux equation includes both heat and electrical affinities. This leads to the conversion of heat directly into electricity at the junctions of different types of materials. This is how thermocouples work. For example, if you've got thermal gradient across the material that produces an electrical current. And the usual engineering way for expressing the Seebeck effect is in terms of the electromotive field here, the EMF, is equal to our thermodynamic driving force, which is a temperature difference. Following Onsager, this would actually be expressed in terms of a reciprocal temperature difference, but this is just how it's captured from an engineering point of view. The strength of the coupling is the Seebeck coefficient here, epsilon. If the epsilon is 0, then that means there's no coupling, so you would not have a Seebeck effect. And if it's non-zero, then you will have a Seebeck effect. The opposite of that, which is really the same fundamental process, is the Peltier effect. This is a thermodynamic or thermoelectric effect in which heat is emitted or absorbed when an electrical current passes across a junction between two different materials. This is used to make thermoelectric heat pumps or cooling devices. So here we're applying an electrical potential gradient and getting the flow of heat. So it's just the inverse of what we did with the Seebeck effect. But if assuming Onsager reciprocity is valid, the strength of the coupling is the same between those two effects. Another variation on this theme is the Thomson effect. With the Thomson effect, there's evolution of heat as an electric current passes through a material with a temperature gradient along its length. And this would be a thermoelectric material with a superimposed temperature gradient. So this transfer of heat is superimposed on the common production of heat associated with electrical resistance. And the key thing is that with the Thomson effect, the Seebeck coefficient is also a function of temperature. One final example is electromigration. Here we've got the transport of material in an electrical potential gradient. And this results from a momentum transfer between the conducting electrons and diffusing atoms. So if you've got, say, copper diffusing here, the copper can have interactions with the electrons where they transfer momentum between each other. And as a result, the flux equations involve both mass affinities as well as electrical affinities to capture that coupling effect. And there are plenty more examples in the book if you want to check it out, including example problems at the end of chapter 2. But to summarize today's lecture, nearly all real processes are irreversible processes. Irreversible processes result from a non-zero affinity, which is the thermodynamic driving force, and they produce a non-zero flux, which is the time rate of change of a thermodynamic coordinate. Irreversible processes increase the entropy of the universe and are therefore agents of the second law of thermodynamics. The rate of entropy production is just the product of the affinity and the flux. And if you sum up all those products of affinities and fluxes, you get the total rate of entropy production. We made 3 assumptions in our treatment of irreversible thermodynamics. It was a purely resistive system, a linear system, and Onsager reciprocity. The Onsager reciprocity theorem defines the inherent symmetry in governing the driving forces in irreversible processes. So next time we are going to dive into chapter 3, and that covers Fick's laws of diffusion. We're going to start from Onsager's formulation of irreversible thermodynamics, make the necessary assumptions to obtain Fick's first law. We're going to use Fick's first law and the conservation of mass to derive Fick's second law. And then when we get ahead to chapter 4, we're going to be solving Fick's second law under a variety of conditions. So I will see you then. Till now, or till then, hope you enjoyed the lecture and let me know if you have any questions at all. Thanks, everyone.